I did not get to on Tuesday was the last part of thermodynamics. So I want to finish that up and then I'll do a brief review. So if you have questions and stuff, then we can discuss it. And then we'll go to the quiz and wrap up. So the thing that we didn't do is in the notes. That's in the thermal properties of matter category. So we were doing several things in thermal properties of matter, and this is essentially what we would characterize as thermodynamics. And I briefly alluded to thermodynamics on Tuesday. So let me just elaborate. The material here is more conceptual at this stage rather than deeply calculational, because the calculations here are not simple. So the easiest way to understand it, those of you who have had some chemistry probably know this already, but you can take some kind of a container, let's say, it doesn't matter what the detail of the container is, and let's say you have some lid on it. So the lid can fluctuate. So you can press this lid to apply pressure. That's the basic idea. Or if the gas here has high pressure, it can raise this lift, much the same way as steam would push up the lid of a kettle. So here you have, let's say, a gas, and there is a certain volume V. You can apply a certain force from this end or that end, so therefore there is pressure associated with the existence of something which can be moved. In this case, the lid can be moved, right? So that basically means that the pressure can fluctuate. Okay? So for example, if you heat this up, then the gas can expand. And if it expands, then it would push this piston up. If you cool this down, the kinetic energy of the gas molecules will go down. And if it goes down, then the gas will try to take less space, which means this piston will go lower. So the critical thing here that we hence need is temperature T. And T here is expressed in absolute scale. T here is not expressed in centigrade scale. Okay? So if it's given in centigrade scale, make sure before you do calculations, you convert that to absolute scale. So typically when you have a complicated system like this, you do some simple experiments. For example, you can look at how pressure varies with volume. And this is relatively easy because you know that pressure and volume would be inversely related. So how pressure varies with volume, but because you have three variables, you must keep one of the variables constant to get a good idea. So you must say what is constant. Temperature is constant. So if you hold temperature constant, if you change pressure, how does volume change? Or if you change volume, how does pressure change? It turns out that pressure will go inversely as volume. So if volume is large, typically that would mean pressure would go down. And if volume is small, typically that would mean the pressure would go up. This is the case of a relatively simple gas. And you will see this behavior in almost all gases. Now, when you hold temperature constant, there is a name for it. Don't get nervous if you see the name. It's called an isothermal process. So just a name, but it's an important name regardless. An isothermal process means that there is no change in the thermal environment. The temperature is fixed. So pressure goes inversely as volume. So we can ask the temperature, how does pressure vary with T? But how pressure varies with temperature T, this should be done with volume constant. Otherwise, things will become unwieldy. So volume constant also has a name, but let me not get into that. So P varies as T. Actually, if you increase the temperature, the pressure will go up. And that's also very intuitive, because if you increase the temperature, the kinetic energy of the gas molecules will increase. And if the kinetic energy of the gas molecules will increase, they're moving around faster, they're hitting this point, that point harder, and therefore the pressure will naturally go up. So furthermore, we can also see that pressure with, the other thing is that volume also will increase or decrease with temperature if pressure is constant. So all these beautiful relationships are actually very simple in this case, and they're fairly accurate. Okay? So these are fairly accurate descriptions as it turns out. So V is proportional to T. Furthermore, it won't be a surprise to realize that V will be proportional to the number of moles of the gas. So what is the number of moles of a gas? So that I denote by N. N equal to number of moles of the gas. So basically that's the atomic number in kilograms having how many atoms? The number of atoms is, so 1 mole contains 6.023 times 10 to the power 23 atoms or molecules, whatever. So this, of course, is what is known as a universal constant. It's a very weird thing, and it's what we call Avogadro number. So if you take a mole of a gas, then the amount of material, the number of molecules and atoms that the mole will have is actually a well-known number. That is Avogadro's number. So therefore, if you increase the amount of material, clearly the volume will increase. So that's not a big surprise. And the very same thing will happen as far as pressure is concerned. If you put in more atoms and molecules, pressure also will go up. There are all these variations that you can actually check in the laboratory, and that is not necessarily a very difficult thing to do. So therefore, one can now try to put this entire story together, and if you do that, then one way of writing it would be P varies inversely as volume, P varies directly as the number of moles N, P also varies directly as temperature. So these are the things that we can put together, or alternatively we can write PV is proportional to NT by multiplying both sides with V, right? So this one has a slightly appealing form because pressure times volume is energy, and this also will have an energy scale. And to get it the right energy scale, you need some kind of a constant here. So let's say then that this constant we denote by R for historical reasons, or NRT, that's a more common way of writing it. And it turns out that this R is a universal constant. So just like the speed of light is a universal constant, just like big G in gravity is a universal constant, this R is also a universal constant. Now you might be surprised that how come that I take any gas and just do some simple checking of how pressure and volume varies and how temperature and volume are related, and what pops out is a universal constant. It's a constant anywhere in the universe. Well, part of the reason may be that material is material no matter where you go in the universe. So it is not therefore a huge surprise that when you start dealing with macroscopic properties of materials, you actually end up with a universal constant. And the value of this R is 8.3 joules per degree Kelvin. Again, Kelvin is a universal scale, we know that. So 8.3 joules per degree Kelvin is therefore an important constant. Now, why did I do this? Why did I actually tell you this story of PV equals nRT? The reason is, at the simplest level, when we do thermodynamics, which essentially concerns behavior of bulk matter, okay? So by bulk matter, this can be steam, steam going to water, that would be a bulk matter going to a phase transition. We discussed a little bit of that last time. But if you consider this bulk matter in the gas phase, then again, you actually can dig deeper and try to decipher what the properties of this bulk matter is. And that gives you some amazing capabilities. One of the amazing capabilities that you get is ability to calculate work done by a gas. Now, at the face of it, work done by a gas, just like work done by anything else that we have studied in, for a while now, is no big deal, right? But as I mentioned briefly, I think in my last lecture, work done by a gas is a transformative thing and has been a transformative thing to human civilization, because it was the ability for gases to do work that allowed us to develop the first engines. And so that ushered the beginning of the machine era, where engines and machines could do our work. And therefore we could do things that we could never do before. So this is why thermodynamics turns out to be an important subject. And furthermore, what is also an important subject is what's at the nuts and bolts of thermodynamics. At the nuts and bolts of thermodynamics, we would like to understand how atoms and molecules interact, and whether from that interaction we can construct equations like these for more complicated scenarios. Because this is a very simple scenario. PV equal to nRT should be valid in some sense, in some broad scale. But it's so simple that there is no guarantee that it's always valid, number one. Number two, it's only valid in the gas phase. What about when the system changes from the gas phase to a liquid phase? There we need more physics than what I've given you so far to be able to dig deeper. So a broader understanding of matter requires us to go deeper. But thermodynamics has historically turned out to be an extremely useful subject. But what is even more interesting, that you will almost never find in a textbook, is that the relationships that you have in thermodynamics, the simple proportionality type relationships with different variables, allow you to describe stuff that you otherwise would not be able to describe. One of them would be the financial model. Very similar mathematical relationships can be developed to describe the financial model. Not as simple, but more complex. But structurally, this kind of simplistic mathematics can allow you to dig very deep into areas that are totally different. Another area, you wouldn't believe it, are elections. Elections have thermodynamic behavior, of course with different variables. There are many other examples I can give you guys, but this kind of macroscopic behavior-based analysis is often done in many areas. People in the business world use it quite often. They're used to predict elections. So, kind of fun stuff, actually. Yeah?
For Sidner, don't you need the other value of R as well?
What is the other value?
0.08206.
That's in what units? In another unit, right? Yeah. I just gave it in one. You can look it up somewhere. Yeah. So, this is just in joules per degree Kelvin, and since we have, so you're talking about calorie and all that unit. Yeah, right. Okay. So my message therefore is that this kind of an equation which we actually call an equation of state. Equation of state. So if I say equation of state in a question, you should immediately understand that in this case I only mean PV equals nRT, because that's the only equation of state that we'll be playing with. Okay? So equation of states are therefore very important. You can have an equation of state for a gas. You can have an equation of state for, for almost any material you can imagine. You can have an equation of state probably for a political system. So these equations of states therefore describe these macroscopic variables: pressure, volume, temperature, and macroscopic variables. They can be easily measured in the laboratory in daily life. But yet they tell us about behavior of atoms and molecules at the finest levels, at in some gross sense. So the use of equation of state, we often use it then to calculate, in physics and thermodynamics, to calculate work done. Okay? Work done. How much work a gas can do. Now you can ask the question, how valid is it? This super simple relationship that you have pulled up here, PV equals nRT, how valid is it? It turns out to be quite okay for most dilute gases. So PV equals nRT works reasonably well for most dilute gases. So that then means if we have a dense gas, if we have a charged gas, then it may not really work. And that is more or less true. Okay? If you have complicated gases, then it probably won't work very well. I can give you one example, for instance. I think I may have mentioned it, but about 25 years ago or so, above the Antarctic, the Earth had a massive hole in the atmosphere, and that hole was the ozone hole. So essentially Earth's ozone layer, which is not a very thick layer, it's a very fragile layer, got depleted. Now this is a big deal for us, because when ozone gets depleted, the harmful solar radiation, the UV radiation, gets in higher doses. And when that happens, it is very dangerous for humans, because humans cannot withstand UV radiation. I think there is DNA damage, there is certainly skin damage. It increases the death rate significantly. So there was a great deal of concern that was immediately raised regarding this ozone hole that was seen from the satellite. And it was determined that the ozone hole was caused by freon that's been very, very heavily used for refrigeration. The freon was basically killing off the Earth's very thin ozone layer. So what was done was that we eliminated the use of freon from refrigerators. So your car actually should not be using a freon. Actually, it uses something else, as long as it's a car which is more than less than 25 years old now. None of the refrigerators that you see actually would be using freon. But in the old days, you used to use freon. Many of the old refrigeration units in homes still use freon. So anyway, so how was freon developed? How was the replacement of freon developed? The replacement of freon was developed because it was figured out what kind of an equation of state is needed, such that the ozone damage could be minimized. And then the material was developed by doing back calculation of what is needed, such that it didn't have the bad properties that freon had. Freon didn't have this equation of state. But so they came up with the right equation of state that they needed, such that it could work as a refrigerant, but it wouldn't damage the ozone layer. So that had to be synthesized. And a great deal of that work was actually done in Buffalo by a company called Allied Chemical in those days, which is now owned by United Technologies, which is of course a very large company that you may or may not have heard of. But Allied Chemical, I think Allied Chemical may actually be owned now by Honeywell. But Allied Chemical was the company, and I knew the group that did the work because I had invited them to give a lecture on that problem right in this room about 15, 20 years ago. So anyway, so this is very, very interesting and very important, even important for our own survival, if you will. Now, I talked about work done, but why do we care? Well, just like in every other field of physics, in thermodynamics, there are laws too. Okay? We have learned about Newton's laws, right? First law, second law, third law. In thermodynamics also, actually, there are 3 laws. We won't be dealing with all of the laws. So the main laws that we'll be dealing with is the first law. And then there is the second law, obviously. It's a no-brainer. But what you don't have in mechanics, in thermodynamics, people figured out one law was missed. And that's called the Zeroth Law. I'm not kidding. It's seriously called the Zeroth Law. So Zeroth Law basically says the following. It says that if you have 3 bodies, let's say, and they can somehow interact with each other, then if one has a certain temperature, all of them will acquire the same temperature. That's basically the message of the Zeroth Law. Zeroth Law technical statement is not the simplest. So when I teach a graduate StatMech class, which Rance has taken, if I recall correctly, I go through the technical development of Zeroth Law. But the idea of Zeroth Law is that if 3 reservoirs are connected, and we know the temperature of one of them, then all of them will acquire the same temperature. So this will acquire the same temperature. If this is somehow linked to that, that will also acquire the same temperature and so on. So in other words, temperature has a tendency to distribute itself in such a way that it minimizes heat flow. That's what it does. Okay, so that's the message of Zeroth Law. So this is a very simple law too. This is an energy conservation law. So an energy conservation law essentially has to do with total energy being the same. And since we are doing thermodynamics, we are talking about stuff like heat, right? So the content of this first law is as follows. Delta Q, that is the heat in or out of a system that's one side of the equation, is equal to delta U, this is a very complicated thing, plus delta W, which is the work done by the system. So you can immediately see why we need the equation of state. Because if we do not know the equation of state, we cannot calculate work done. Okay? So you have to have the equation of state somehow to be able to do work done. By the way, this equation of state for the most dilute simplest gas is not all the knowledge that we need for work done calculations. We need more. So there are systems which you can design which are so insulated that heat can neither come in nor leave the system. And when you have changes of pressure, volume, and temperature in such systems, where no heat can come in and leave the system, they are called adiabatic systems. And adiabatic systems, they actually have a different equation that they must satisfy. So I won't take you there, but I just want you to be aware that the equation of state is not the be-all and end-all of everything, because you have to also know typically the adiabatic story, which we don't get into here. At any rate, I have given you one way in which you may be able to calculate delta W, and that would be somehow to be able to compute how pressure and volume would change. So I'll come to that in a moment. Delta U typically is a change in internal energy of the system. Bless you. So this is a little bit more difficult to calculate. change in internal energy of a system almost always depends very strongly on the absolute temperature and its changes of the system. So if the absolute temperature changes, then delta U will change. So in isothermal processes where temperature would not change, this thing may not actually change very much. So that's just to give you an intuitive feeling of how this works. So our typical goal then, one of the challenges that one would face would be how to calculate delta W. So at the peripheral level, we already know that delta W, which is the amount of work done, is some kind of a force times delta X. You know, of course, vectors and all that, and let's say we write it like that if needed, but we understand that it's just F delta X in one dimension. Meaning along the line. So at this point, actually from dimensional considerations, you can already see that if I write the following, then this A and A will cancel, but F over A gives me pressure. So therefore, instead of writing F dot delta X, I can actually write it as P dot delta V, or P delta V. So one way of calculating delta W would be to know P delta V. But P delta V may not be so easy to get, you see, because P doesn't remain fixed if V changes. So P therefore has some dependence on V. So when I write P as a function of V, I actually mean that. P has some dependence on V. How do I know that? Well, I know that because I have an equation of state which says P is inversely proportional to V. PV is equal to that. But P and V are inversely related. So I need to know some kind of so this is where the equation of state would come in. And this would then happen in a process where temperature is constant. So I know, for example, that PV equals nRT. If I hold T constant, this is a constant, that's a constant, that's a constant, then I know that P is equal to nRT over V. So then I should be able to write this as, in that case, let's say, nRT over V times delta V. There you go. Now you need calculus. Now you're cooked. And if you integrate that, you get a logarithmic function, right? But I can give you the formula. So if you actually work it out, so if T is constant, then delta W will be nRT. It turns out log of the final volume over the initial volume. That's the formula in all books have. It's trivial to derive if I actually do an integration, but of course that I won't do that. Now if it so happens, if P does not much depend on V, then of course we can write delta W as simply P times delta V. But that's only in the very special case if P doesn't much depend on V, but usually P would depend on V by some kind of an equation of state. So most of these problems therefore deal with this kind of general structure, and that's what I wanted to introduce you to. Now let me stop the discussion of thermodynamics for now by telling you a little bit about these kind of pictures on a PV plot, pressure volume plot. So on a pressure volume plot, you can think of processes in which, let's say, so this would be an isotherm. So what is an isotherm? Remember, an isotherm is when the temperature is fixed. I actually introduced that word somewhere here. Isothermal process. Remember I said if temperature is constant, you have an isothermal. So let us say that temperature is some T1 here, and temperature is some other temperature T2 here. So therefore, this is an isotherm with T1 constant, and this is also another isotherm, but now with T2 constant. And this shouldn't surprise you because this is nothing but a hyperbola. And that's exactly what you should expect because you already know that P is equal to nRT, all of these are constants, divided by V. So that's an equation for a hyperbola. So essentially what it says is that if volume shrinks, pressure becomes very, very large, and if volume increases, pressure becomes very, very small. That's really what this dependence does. So in a PV diagram, the reason why it's convenient then is you can actually see these isotherms. So I can actually take a system, I can design a system, a gaseous system, let's say, or in this case, and I can take it to some point here at a certain temperature T1, and I make sure that it has a certain pressure and a certain volume such that it satisfies my ideal gas law for simplicity, whatever is the equation of state. And let's say now I keep the temperature fixed and let it expand, go like that. Okay? So physically what I'm doing is, I have the system, and the system is in an oven, so it's in a place where the temperature is fixed, oven temperature is fixed, let's say at 350 degrees, and as a result, what will happen now is if I hold the temperature fixed, this thing actually will expand and the pressure will fall. And that's the reason why I have drawn that line over there. Let me try to use maybe another color there. Like this. So this is a process that you can actually do. But as I told you, there is also another thing that these systems have, which is this adiabatic thing. In which case, no energy enters or leaves the system, but the system's variables can change. An adiabatic equation of state, which I did not give you, is different. And if I were to draw an adiabatic behavior here for my same thing in the oven, so no energy enters or leaves the system, it will kind of look something like this. So let's give it a name A, B, okay? And this is point C. I've come to. Now instead of putting it in the same oven at temperature T1, I make sure it's in an oven with temperature T2, and T1 is larger than T2, so now it is in a colder environment. And in this colder environment, I let it contract, which it would like to anyway, up to some point where it would like to go to, such that my volume will shrink as it contracts, and temperature is held fixed, so therefore the pressure will ever so slowly rise. So now I have come to the point B, and if B is the right location, I can again arrange for an adiabatic treatment where no energy enters or leaves the system, and that would actually take me back to this point. This is called a thermodynamic cycle. Why am I doing this? The reason why I'm doing this is because this is the process that every engine has. Even the engine in your car has something similar, usually more complicated. The steam engine that was invented by James Watt back in 17-something. All of these engines essentially use this thermodynamic cycle. Why? And the story is fascinating. So this is what the Industrial Revolution gave us. In this case, when I hold the temperature fixed and I let the gas expand, it actually takes in heat. This is your delta Q, if you will, in the first law statement. So let's say it takes in heat Q1. During this adiabatic expansion, it actually does work. Delta W, then it gives off the energy it couldn't use, Q2, and then goes back. So essentially what it is that, the work is done actually during this expansion and then it contracts off. The adiabatic just takes it from B to C without any energy change, and this D goes from this adiabatic takes it from D to A when there is no energy change. But Q1, which is more than Q2, Q1 minus Q2, is basically going to give you some kind of internal energy change and some kind of work done in this case. So this is your delta Q, and this would be a simple thermodynamic cycle. And this particular cycle was by Sadi Carnot, who was a French engineer, and it has a name, the simplest cycle actually, it's called the Carnot Cycle. You'll often see that name pop up in many textbooks dealing with this subject. Okay? So you're essentially, so what I did for you is sketch for you the Carnot Cycle as one of the simplest possible thermodynamic cycles that allows you to design an engine. Okay? Yeah.
Is this how it would run on hydrogen if you're talking about gases and such?
All engines essentially that uses some kind of a gas or a hot fluid would end up using some kind of thermodynamic cycle. Most thermodynamic cycles that we use for modern engines are actually very complicated. But that's why I've been emphasizing that this is the simplest engine you can make. So, I mean, the chemical engineers would be able to tell you a great deal more about the currently used thermodynamic engines. Yeah. Say that again. Q1 and Q2 are equal. Okay. So that's a very good question. So if Q1 and Q2 are equal, then you have a terrible engine because it didn't do any work, right? So that may be not so hard to do, just make a bad engine and it will actually make Q1 and Q2. But what is also interesting is, can there be a situation where Q2 is 0? So can you take all the energy from a heat bath and convert it to work? And the answer is, there is a law in nature that says that's not possible. And that basically takes us to what I did not do, which is the second law. It takes us towards second law. Second law of thermodynamics actually is a very complex law with many different facets. It can be mathematically stated in one line, but I'm not going to explain it to you guys because, first of all, it's not necessary unless you have a specific question. I'll get into that. But suffice it to know that that nature disallows making of an engine where you take Q1, you convert everything to work and reject no heat to the colder bath. That would be an engine with incredible efficiency, with the highest possible efficiency, and that causes some fundamental problem with the argument, which basically would mean that you can go down to 0 temperature. That's the net result of if that were to happen. And reaching 0 temperature is essentially impossible because we cannot freeze out all motion. So there is a fundamental reason why that is not possible. But that said, we can make engines very, very efficient, of course, and that should not be a big surprise. I mean, one reason why we are stuck on using something like petroleum for most of our engines even now, although things have changed quite dramatically in the last 15 years or so, is because petroleum-based engines turn out to be very efficient. So naturally, efficiency at the end of the day means that there is a price advantage, and so any kind of a mass scale change means it becomes expensive. But now, of course, things have changed because the efficiency of various cleaner technologies has gone up substantially, and so the dividend that you used to get is not much there. Let me put it that way. I mean, I have 22 solar panels on my roof, and I can tell you that my electricity bill, which used to be quite substantive, has more than disappeared. So, you know, and it was not cheap, but it wasn't something that was economically unaffordable because it pays off. All right. So basically, I spend about for the 22 panels, my out-of-pocket cost was about $10,000. Now, $10,000 is a lot of money, but I'm paying that $10,000 essentially with very tiny interest, about 2%, over a period of 15 years. So, in effect, if you think about the amount of payment I make per month, that is less than my average electricity bill. So there you go. That's my argument. So it has changed. But anyway, so this is how engines are designed. So let me not get deeper into this, because as long as you understand that there are isothermal processes, adiabatic processes, and the thermodynamic cycle, and as long as you understand the basic idea of a thermodynamic cycle is doing work, and that's how engines are fundamentally designed, that's good enough for me. As long as you understand that there is a first law, which is the energy conservation law, and delta Q is delta U plus delta W, that's good enough for me. As long as you understand delta U is only temperature dependent, that also is good enough for me. Delta U calculations, as I said, are a little bit hard. And delta W calculations are stuff that we often end up doing. The ideal gas equation of state, of course, is somewhat important, so I would encourage you, if you have any issues, to get it clarified with me. So let me spend a few minutes talking about the stuff that I want you to go over. They're all in the review sheet I posted, so I'm not going to tell you probably much new. But let's start with, okay, so one of the things that I told many students who asked me was, since this exam is supposed to be comprehensive, the way I have tried to do it in most years, and I think I'll do the same this year, is I'll divide the questions into two categories. So one category would be longer questions, which would be like the typical problems you have done so far in exams 1, 2, and 3. So you know what to expect. Those are the kind of problems that I will cover in the longer category, and that's supposed to be pretty comprehensive. So those questions would essentially span from, you know, kinematics, so chapters, the early chapters, where we had all the kinematic formulas, people screw up projectiles a lot, so make sure that you remember how to do projectile problems split up into X and Y, you relate X and Y variables with time, the equations that come around and how to solve them. Right now you'll probably find them pretty easily because you have done much harder stuff. But regardless, don't ignore it. It's a favorite for all of us to ask some projectile problems. Newton's laws, well, Newton's laws, you shouldn't have much trouble, but I find that people still stumble and fumble when you're setting up the free body diagrams and the force equations. So make sure that you have given your due respects to those equations. Make sure you go through all the weird examples that we have done and all the not so weird examples we have done in class. Circular motion and gravitation, centripetal acceleration, centripetal force. This stuff is very non-intuitive because you are working with things that are going in a circle. So that means you are in an accelerated frame of reference. And so most of the calculations that we have done require some level of special thinking. So I would urge you to review that chapter very, very carefully. If you have questions, please do ask me, and copy Rand's and Rufain's. If I'm somehow occupied, they can give you a quick response if they are available. I cannot underemphasize work and energy. Work and energy is critically important, and we really use that very freely after that period once we did it. So work and energy be on top of that. Momentum conservation is relatively simple. So my only request, if I ask you something on momentum conservation, do not screw it up. That's a gift. If I ask you on gift questions like momentum conservation, projectiles, if I ask you questions on simple stuff like things going around in a circle and gravitation, Kepler's laws, don't screw them up. Because historically, the final exam is where a lot of people do poorly. They do poorly because A, they become overconfident. B, they think they're doing great and they can screw it up, which actually hurts them because that's 14% of the grade straight off the bat. So I have been disappointed historically with final exam performance, so I just want you guys to, in very polite language, not screw it up. Okay? Rotational kinematics and dynamics, that's obviously very important, but rotational dynamics is obviously more important because I really want to make sure you guys can calculate torques. So you should know what I mean, or what we mean when we say you take the force and the perpendicular distance of the force from some fixed point. Do not screw up perpendicular distance. You should be dreaming perpendicular distance between now and the final exam. Okay, so be careful there. And equilibrium problems with torque, ladders, stuff hanging off the window, all kinds of nonsense like that are favorites of us professors. Simple harmonic motion is not simple, so make sure that you can go from the equation of motion. So F equals minus kx, F is ma, so ma equals minus kx. So acceleration and x are related. Spring constant is important. If you know k and m, you can get the omega. T is 2 pi over omega. Omega is square root of k over m. These are things that you shouldn't have to think about. Small stuff about sound problems. Now we are getting into the smaller problems. I told you I'll give you longer problems like you've seen and the smaller problems. So oftentimes simple harmonic motion can be a part of a smaller problem. These are typically, they carry less points, but if the others carry, let's say, 20 points, this can carry 8 or 10 points. So they're at least half as important. So simple harmonic motion in that category, sound propagation in that category, fluids in that category. Be sure you understand Archimedes' principle. Be sure you understand Pascal's law. Why there is a minus sign. P2 minus P1 is minus rho y times height. Why there is a minus sign? As you go up, because gravity is downward, pressure goes down. That's why there's a minus sign. So these things should be clear in your head. Bernoulli's equation. You should be dreaming Bernoulli's equation. Now, as far as heat and thermodynamics are concerned, we have actually done quite a bit. We have done phase changes, and I've given you problems on phase changes, so you're practiced on that. I haven't given you problems on heat flow. So conduction, convection, radiation. Radiation is Stefan Boltzmann law. So these things you should know, you need to know. This is where the small problems come in. And as far as what I did today, first law and the equation of state, what they mean, I'm interested not so much in whether you can do algebra. I'm interested in whether you understood what I talked about today. So make sure that you are on top of that, okay? Any questions? Yes. Values for what? Louder. No, I'll give you those numbers. So don't strain your brain trying to remember those numbers. Yes. So long questions typically about 4, and shorter questions maybe about 4, around there. That's a ballpark. Huh? What? The 3 modules? Yeah, I have to ask you some nonsense about it, so I will. But it's small. Okay, so go through that. It takes a lot of time. Don't try to do it on Sunday. You will never finish it. It does take time. It is a pain in the butt, but get it done. Because I am obligated to ask you something. So since people do badly in finals, why make that possible for you to have? Any other question? Huh? Very little. Of the order of 5, in that range. Something very. I don't think that's very important. But I'm supposed to ask a few things just to make sure that students have been tested on it. So that's the principle. All right, I've enjoyed having you guys. So we'll go to the quiz now since I'm done.